In a previous video, I've talked about arithmetic progressions or arithmetic sequences. If you haven't already done so, I would advise looking at that. But I'm just going to quickly recap the basics of a sequence and the notation that we often use. So a sequence is just a set of ordered numbers or a list of ordered numbers. So for example, 1, 3, 5, 7, and so on. There is some kind of order to it. In this case, we are adding 2 each time. A general sequence can be represented using A with a small subscript number to show which term you are on. So A3, for example, means that we are on the third term, A4 and so on. We use ... to show that it continues, and then if the sequence actually ends, we can use an AN to show that this is the nth term, which could be used for any term in the sequence as a general term, or it is often used as the last term of a sequence. Now, for the first term, we often don't bother with the 1, it will just be an A. So A on its own means the first term, AN means the nth term, and it is important that you understand the difference between N and AN. N is the position or term number. So for example, a sequence, the position just goes 1, 2, 3, 4, and so on up to the nth position, and the value of the term. So if we look at our sequence that we use as an example up here, the first term A1 would be 1, the second term 3, third term 5, fourth term 7. So N is the position that the term is in, and AN is the actual value of that term. So it's just important that you really understand the difference between N and the nth term. So for example, in this case, when N is 3, we can say A3, the third term, is equal to 5. So a geometric progression or geometric sequence, GP for short, is just a special type of sequence. So in this case, it is a sequence that each successive term has a common ratio. So for example, the sequence 1, 3, 9, 27, 81 and so on would be an example of a GP because each term is 3 times the term before. So the ratio between successive terms is constant. It is always 3. So another example of a geometric progression would be 32, 16, 8, 4 and so on, because in this case every term is half of the previous terms. So the ratio between successive terms this time is a half. So all a geometric progression does is it multiplies each term by a constant number to get the next term. So in this case that ratio is 3, and in this case that ratio is a half. So rather than an arithmetic progression where the difference is constant each time, in a geometric progression the ratio is constant each time. So if you were given a progression and told that it was a geometric progression, you could work out the common ratio by taking any term. So for example, if I take this term and dividing it by the previous term. So in this case, 48 divided by 12, that will tell me what I need to multiply my 12 by to get my 48. In this case, that is 4. So my common ratio each time is 4, and if we double check, 3 times 4 is 12, 12 times 4 is 48, and 48 times 4 is 192. So we can see that there is a common ratio each time. More generally then, remember we said that A is used as the first term of a sequence. So the next term would be A multiplied by our common ratio, so we will call that R. So R is our common ratio of our geometric progression. Our next term, our third term, would be equal to A times R, our second term, multiplied by R again, so A times R times R. Our next term would be A times R, the same as the previous term, and then multiplied by R again, and so on. So if we simplify this down a little bit, A is just A times R, remember in algebra we often don't write the times sign, so we can write that as AR. A times R is AR squared. A times R is AR cubed, and we could continue on. Now if we compare each term to its position within the term, it helps us to see the pattern that's going on. So N, remember, is the position within the term, so 1, 2, 3, 4, and an is our nth term. So our first term is a, second term ar, fourth term ar cubed. Now it's a little bit difficult to see the pattern that's going on, but remember a is the same as ar to the power 0. This is just making it fit more in line with the other terms, because remember r to the power of 0 is 1, so a times 1 is just a. ar, there is an invisible 1 there, r is the same as r to the power 1. Now all the terms look similar and we can see the pattern that is going on. If we have a general term, the nth term, we know that we're going to have a, and then we're going to have multiplied by r n minus 1 times, so one less time than the term we're on, because the first term we haven't multiplied by r at all, the second term we multiplied by r once, the third term we multiplied by r twice, the fourth term we multiplied by r 3 times, and so on. So the nth term we multiplied by r n minus 1 times. So this actually gives us our first law of a geometric progression, that the nth term of a geometric progression is equal to the first term a, and then multiplied by r one less time than the term we're on, so n minus 1 times. So an is equal to a times r to the power n minus 1. This allows us to find any term we like of a geometric progression, provided that we know the first term and the common ratio. Let's have a look at a couple of examples then of how we can use this. So find the 8th term of a geometric progression that goes 3, 6, 12 and so on. So the first thing we need to do is work out our common ratio of this geometric progression. So remember, we can take any term we choose, so it's always easiest just to take the second term and divide it by the previous term, so divide it by the first term. So our ratio is equal to 6 over 3, which is 2. And just to double check, 3 times 2 is 6, and 6 times 2 is 12. So we have got a common ratio of 2 each time. We also, because we've been given the sequence, a, remember, is always our first term, and in this case it is 3. So we know a and we know r. Remember, we can find any term, an, by taking the first term and multiplying it by our ratio one less time than the term number. So to find our 8th term, we take our first term a, and we will need to multiply it by our ratio 7 times. So a is 3 and our common ratio is 2, so we take the number 3, the first term 3, and multiply it by 2 7 times. That gives us 384. So our 8th term would actually be equal to 384. So we could have done this with any term. We could have found our 20th term by multiplying it by r 19 times. We could have found our 300th term by multiplying it by r 299 times. So if you can remember that rule, it is actually nice and simple. Another example then, in this case we haven't been given the sequence, but we have been told 2 different terms of the sequence. So we've been told that our 4th term is 9. So remember, our 4th term, a4, is equal to 9. And our 4th term would be found by taking a and multiplying it by r 3 times. So we've got one equation here. a4 gives us that 9 is equal to ar cubed. We can do the same with the other term it gives us. The 7th term is equal to a third. So a7, if we think about what that is, that means that the 7th term, which is equal to a third, would be found by taking a and multiplying it by r 6 times, one less than 7. So we now have 2 equations, and if we call them equation 1 and equation 2, we can solve them simultaneously. But because we don't have a added to r, we've got a times r. The way to eliminate a is to actually divide these equations. Now, my second equation has more r's in it, so I'm going to actually do equation 2 divided by equation 1. So if I take equation 2, which is ar to the power 6, and I divide it by equation 1, ar cubed, that is the same as doing a third divided by 9, because ar6 is equal to a third, ar cubed is equal to 9, so these two sides of the equation are the same thing. If we simplify that down, a third divided by 9 is 1 over 27. Either do it in your calculator or have a look at my fractions video if you don't know how to do that. And then ar to the power 6 divided by ar cubed. Well, this a on the bottom cancels out the a on the top. and then 3 of the 6 r's from the top are cancelled out, so we are left with r cubed. So r cubed is equal to 1 over 27. Now before we go on to solve this to find r, it is a good idea to check the sensibility of your answer. You could have actually got straight to this equation from the question, but it is easy to make mistakes if doing so. So it's a good idea to use the simultaneous equations and then check this from the question. So what I mean by that is we are given the 4th term and the 7th term. So we can think, well, how do we get from the 4th term to the 7th term? We go from the 5th, 6th to the 7th. So there are 3 terms between it, which means that we would need to multiply by r 3 times. So our r cubed bit of this makes sense. We are also told that our 4th term is 9 and our 7th term is a third. So how do we get from 9 to a third? In terms of multiplying, what do we need to multiply 9 by to get a third? Well, I know that I need to divide 9 by 27, and that is the same as multiplying by 1 over 27. Remember, a ratio is what we need to multiply by, so we need to multiply 9 by 1 over 27 to get 1/3, and that is equal to our ratio used 3 times. So this equation does make sense in terms of our question. And to get r on its own, then we need to cube root. So r is equal to the cube root of 1 over 27, which is 1 over 3. So our common ratio this time is a third. And just to double check that that makes sense, from the 4th term to the 7th term the numbers get smaller, so we would be expecting a ratio of less than 1. So now we know what r is, we can use our equation for a4 to find out the first term a, because we know that 9 is equal to a times r cubed, and we remember now know that r is a third. So 9 is equal to a times a third cubed. A third cubed is 1 over 27. So if we multiply by 27, we get 9 times 27 is 243 equals a. So our first term is actually equal to 243. We haven't quite finished the question yet because we are also asked to find the 11th term. So to find the 11th term, nice and simple now, we know that we just take our first term and multiply by our ratio 10 times. So we take 243 and multiply it by a third to the power of 10, and that gives us 1 over 243, which you could convert to a decimal, but I find it's always best to leave these answers as a fraction unless told to do otherwise, because it is more accurate. So pause the video, check your understanding and have a go at these 2 questions. So question number 1, we are given the geometric progression, so we straight away know that our first term is equal to 2, and we can find our ratio by taking any 2 terms and dividing the second by the first. So in this case I'm going to take 3 and divide it by 2. I could have taken 4.5 and divided it by 3. 3 divided by 2 is 1.5, so my ratio is 1.5. So then to find the 13th term, all I need to do is take my first term and multiply it by r 12 times. So that is going to be 2, our first term 2, multiplied by 1.5 to the power of 12. And if you put that into your calculator, that will give you 259.5 to 1 decimal place. So number 2, this time we are told the second term, which is minus 8. And we are told the 10th term, which is minus 2048. So to find the second term, we take our first term and multiply it by r once, and to find our 10th term, we take our first term and multiply it by r 9 times. So now I have my 2 equations, and I can do equation 2 divided by equation 1, which gives me minus 2048 divided by minus 8, and that will be equal to ar to the power 9 divided by ar. So simplifying it down, minus 2048 divided by minus 8 is plus 256, and on the right hand side the a's cancel out, one of the r's cancels, so we are left with r to the power 8. So now to find r, we need the 8th root of 256. And remember, whenever you have a positive root, the answer can be positive or negative. So in this case, there are two possible answers. We can either have r equals 2, because 2 to the power 8 is 256, or r is equal to minus 2, because minus 2 to the power of 8 also gives you plus 256. So there are actually two possible sequences in this case. So now we've got our two possible values of r. For each value of r, I'm going to work out the first three terms of my sequence. So when r equals 2, I know that from my second term being minus 8, I know that minus 8 is equal to 2a, which gives me a is equal to minus 4. So this sequence then would be minus 4. Then my next term would be 2 times that, so minus 8, which gives us our second term for our question, so that's correct. And then our third term would be 2 times that, so minus 16. And if we carried on up to our 10th term, we would find it would be minus 2048. If we have a look at our situation then when r is equal to minus 2, this time we know from our second term being minus 8, we know that that is equal to minus 2 lots of our first term. And that this time gives us that a, our first term, is equal to plus 4. So our sequence then, our first term is 4, multiply that by minus 2 to get our second term, minus 8, multiply that by minus 2 to get our third term, plus 16. So you can see a comparison of these two sequences. The size of each term is the same, but in the first case they are all negative. In the second case, because we have a negative ratio, they fluctuate from being positive to negative. So if we went up to our 10th term, they would both be 2048. In the top sequence, it would definitely be negative because all the terms are negative. And in the bottom sequence, it would also be negative because it fluctuates from being positive, negative, positive, negative. So every even term is negative. So there are actually two possible sequences that would have a second term of minus 8 and a 10th term of minus 2048. So in this question you would have two answers. However, if it was a practical question, it might be that only one of these sequences makes sense. It is rare that a negative ratio makes sense in a practical situation, although it can do, so don't discount it. So let's have a look at geometric series now. A series is just a sum of all the numbers in a sequence. So a geometric series is the sum of all the numbers in a geometric sequence. Now remember, a geometric sequence, our general sequence is A, AR, AR squared, AR cubed, all the way up to our last term, which would be AR to the power n minus 1 if we had n terms in our sequence. So if we were finding the first n terms, we use the notation S with the subscript n. So Sn means the sum of the first n terms of a sequence. So if we are finding that, we need to just add each of these terms together all the way up to our nth term. Luckily, there is a method that we can use where we don't have to physically work out every single term and then add them up. There is a clever way of doing it. If we multiply our sum by r to begin with, that means that we need to multiply every single term by r. So a multiplied by r is ar. ar multiplied by r would become ar squared. Ar squared would become ar cubed. Ar cubed would be ar to the power 4, and so on, all the way up to ar to the power n minus 1, which if you multiply it by 1 more r is just ar to the power n. Rather than multiplying by r n minus 1 times, we are now just multiplying by r n times because we have multiplied it by 1 more r. So now, if we take our second sum, our r times the sum of the sequence, and take away the first sum, which is just the sum of the original sequence. So we are taking this second one, taking all of the terms in the second sequence and taking away all of the terms in the first sequence. So if we start with the terms of the second sequence and take away the terms of the first sequence, we can see that this AR is going to cancel out the AR in our first sequence. The AR squareds will cancel out, the AR cubes will cancel out, the AR4 would cancel out with the term that would be here, and the AR to the power n minus 1 would cancel out with the term before the AR to the power n. So we are actually just left with AR to the power n from our bottom sequence minus A from our top sequence. So we end up with R times our sum minus our sum is equal to AR to the power n minus A. In this format it's not completely useful, but what we can do is factorise out the left hand side. So we know that we've got R minus 1 lots of our sum. We have R lots of our sum minus 1 lot of our sum. So we've got R minus 1 lots of our sum. I've just factorised out the Sn out of the bracket. And I can actually do the same on the right hand side as well. I can factorise out my A, and that would leave me with Rn lots of A minus 1 lot of A. Now I want to know what my sum is, so I want that on its own, so I just divide by the brackets on the left hand side, and that leaves me with A times R to the power n minus 1 over R minus 1. So this is actually our formula for the sum of a geometric series, and it can be very, very useful because it means that you don't have to work out every single term and add them together. You can just plug what you know into this formula. So let's have a quick look at a couple of examples of how we can use this. So in this question we are asked to find the sum of the first 8 terms, and we are told the geometric progression. So we are trying to find the sum of the first 8 terms. We know that our first term A is going to be equal to 2, and we know that our ratio is equal to any term divided by the term before it, so I'm going to just take the second term and divide it by the first term, which is 2, and just to double check I've done it right, 2 times 2 is 4, times 2 is 8, times 2 is 16. So we've got a first term of 2 and a ratio of 2. So to find the sum of the first 8 terms, we need to plug it into our formula. So we're going to have A times R to the power 8 minus 1 divided by R minus 1. A is 2, R is also 2, so 2 to the power 8 minus 1 over 2 minus 1. So we've got 2 times 2 to the power 8 is 256. 256 take away 1 is 255, and 2 minus 1 is 1. So 2 times 255 is 510. So the first 8 terms of this sequence would add up to 510. So in this question we are asked to find the sum of all of the terms of a geometric progression. Now we have been given a ... we have not been given an end to this geometric progression, so this means that it technically goes on forever. There are an infinite number of terms. Now summing an infinite number of terms is only possible if the numbers of each of the terms are getting smaller. If the terms were getting bigger, then the sum would just keep getting bigger and bigger and bigger and bigger. But because they're getting smaller, there is actually a limit. If we have a think about why, if we imagine a bar that is 32 long, our first term is 32. Our next term is going to be half of that. So if I draw underneath, our next term is half of that, it's 16 long, which means that the gap is 16 as well. Our next term then, which is half of that, will fill up half of the gap, which is 8, and that means that the gap is 8 as well because it was half of the gap. That means the next term, which is half the size, will fill up half of that. And then the next term would fill up half of the gap again. Each consecutive term would keep filling up half of the gap. So you would never actually fill up the whole gap. However, with an infinite number of terms, you would eventually reach that limit. So I can see straight away from this that they are all going to add up to 2 lots of 32. So my sum to infinity, we use a little symbol like that for infinity, is actually going to be 64. Now I can only do it this way if my ratio is a half, but if the ratio is anything less than 1, then this does work. As long as it is a positive number but less than 1, then you can find a sum to infinity. And if we think about how we would get that from our formula, so in this case we want the sum to infinity of our first term multiplied by our ratio to the power of infinity minus 1 all over our ratio minus 1. Now you might be wondering how on earth you would put r to the power infinity in your calculator. There is no button on your calculator for infinity, but let's think about what it means. In this case our ratio is less than 1 and it is a half because each term is half of the term before. So we've got r equals a half. Now what happens when you multiply a half by half? It gets smaller. R squared, a half of a half, is a quarter. R cubed would be half of a quarter, which is an eighth. R to the power 4 would be a 16th. So each term is getting smaller and smaller and smaller. If we multiplied it by a half and an infinite number of times, it would get so small that it is practically 0. So we can assume if our ratio is less than 1, then our ratio to the power of infinity will get so small that we can assume it is 0. So in our formula up here, r to the power infinity, we can actually assume to be 0. So we end up with a times 0 minus 1 over r minus 1, which just simplifies down to minus a over r minus 1. So our first term is 32, so we've got minus 32. Our ratio is a half, so we've got a half minus 1. So we end up with minus 32. A half minus 1 is minus a half. And if you divide minus 32 by minus a half, you get plus 64, which is exactly what we expected from our diagram up here. So it does actually work, because remember, the ratio is less than 1. When you multiply something by less than 1, it gets smaller. So as you keep multiplying it, it keeps getting smaller and smaller and smaller until you can assume it is so small that it is practically 0. Some of you might have realised at this point we could actually rearrange this equation, because r is less than 1. If we multiply everything through on top and bottom by minus 1, minus a times minus 1 is plus a. R times minus 1 is minus r. Minus 1 times minus 1 is plus 1. So we could have actually rearranged at this point to a over 1 minus r. Now whether you want to rearrange and then plug your numbers in, because this would have given us the same, we would have ended up with plus 32 divided by plus a half, which is still plus 64. Whether you want to do it that way or plug your numbers in and work it out is up to you, but either way is possible. So pause the video and have a go at working out these questions to check your understanding. So for question number 1, we want the sum of the first 10 terms. So we are going to need our first term multiplied by r to the power 10 minus 1 over r minus 1. I'm just using the formula for the sum of a geometric progression. Now a is our first term, which is just 2, so a is equal to 2. And if I take any two terms and divide them, it gives me my ratio, so I'm going to take my first two terms again. 8 divided by 2 is 4, and just double check. 2 times 4 is 8, times 4 is 32, times 4 is 128. So plug your numbers in. 2 times 4 to the power 10 minus 1 all over 4 minus 1. If you plug that all into your calculator, you get 699,050. So it is actually a huge number in just 10 terms, but that is because every single term is getting 4 times bigger, so they get bigger very, very quickly. Question 2 then, we are told to find the sum of all the terms, which remember is possible because our terms are getting smaller. So in this case, our first term is 27, and our ratio this time is a third, because each term is a third of the previous term. 9 divided by 27 is a third. We want all of the terms, so we are summing an infinite number of terms. And remember, this means that we will be using r to the power of infinity. And because r is less than 1, when we keep multiplying it by itself, it gets smaller and smaller and smaller until we can assume it is 0. So our equation just becomes minus a over r minus 1, which I can multiply top and bottom by minus 1 to get it as a over 1 minus r. You might have used either of these equations, they should both come out with the same answer. A is 27, r is a third, so 1 minus a third. We end up with 27 divided by 2/3, which is 40.5. So this one does actually have a limit, which isn't a lot bigger than the first term itself, but that's because each term is getting smaller quite quickly. So I hope you now understand geometric progressions. Good job, and I will see you again soon.